Welcome to my presentation entitled Practical Perspectives on Brewer's CAP Theorem, Things You Should Consider When Picking a Database That Is Not Relational. A little bit about me. I'm a graduate student at the University of Illinois studying to get my Master of Computer Science degree. I've got a lot of work experience at various companies. I also have professional certifications from several universities and industry certifications as well. A little background before we get started. Relational database management systems were famously proposed by E.F. Codd in 1970. Data is organized into relations or tables with rows and columns. Those relations are organized through data normalization, which typically involves picking a normal form and then organizing your data accordingly. The relations have keys and the columns have constraints which define what kind of data is in the column. There's a well-defined relational algebra that you can use to select and project data from the relations. In more practical terms, there's a query language called SQL, which is well understood and pretty mature now. And there are standards that have been defined like ACID compliance, which tells people basically how a database should act in terms of durability, consistency, isolation, and atomicity. There are lots of working examples that have been around a long time. Lots of enterprise and open source and also cloud examples to choose from. In 1998, at the University of California, Berkeley, Eric Brewer made an observation while studying distributed databases. He observed that distributed databases could have no more than two of these three properties at any one time, those properties being consistency, availability, and partition tolerance. He wrote down his observation as a principle in 1998. He gave a lecture in 2000, making it a conjecture, and in 2002 it became a theorem. Now, when we define consistency, we can say that a consistent database has clients which all have the same view of the data. An available database is one in which the system continues to operate even in the presence of node failures. And a partition-tolerant database is a system that continues to operate and uphold its consistency guarantees even in the case of network partitions. Typically, a relational database has consistency and availability, and we would call that a strict consistency model. Down below, databases which have availability and partition tolerance typically have eventual consistency, and there's a standard evolving around that called BASE, or basic availability, soft state, and eventual consistency. Over the years, the CAP theorem has gotten quite popular with marketing of databases. You'll see in the top left-hand corner a lot of relational databases, graph databases. And then on the consistency and partition tolerance axis, you have things like Bigtable, Mongo, Redis, HBase. And then down at the bottom, on the availability and partition tolerance axis, you have things like React, CouchDB, Cassandra, and DynamoDB. Now, that's not to say that you can't tune the different consistency and availability and partition tolerance aspects of any of the databases. That's why I mentioned it's sort of a marketing thing, but they do sort of specialize in those areas of consistency, availability, and partition tolerance. Unfortunately, what this has led to is a little bit of looking at this as if it's a menu and deciding, well, we don't need to be highly consistent or highly available, so let's not use a relational database. Let's use one of these other databases. And so what I wanted to do with this talk is present a how-to and how to select a database which is not a relational database if you decide that really consistency and partition tolerance are more important, or availability and partition tolerance are more important to you? Because there are obviously a lot of options here, and it's hard to figure out how to choose one or more of these databases for your solution. I just wanted to share a word of caution before we proceed. What do you have to lose by picking a database that's not relational besides your data? One of the most important things to me is you lose 50 years of academic and industry experience. Um, a lot of things have happened in the last 50 years in computer science and, and in the computer industry. A lot of bugs have been worked out, a lot of problems have been solved, and a lot of these newer solutions are still working through some problems that were solved in relational databases a long time ago. Um, in terms of query language, if you're not going to use SQL, then what are you going to use? In some cases, it's not that difficult to learn a new programming language. In other cases, it can be a completely different paradigm. And if so, does your team have the time and energy to do that? Um, in terms of organizing your data, um, are you going to normalize your data? That is to say, are you going to try to organize it in an optimal way so that it doesn't take up too much space on disk? In some cases, no. In some cases, you want to denormalize your data to make the queries more efficient. And that's sort of antithetical to the relational model. For standards, is the database ACID compliant? It's possible that it is, but it's also possible that it's optional and that you need to turn it on. It's also possible that the database developers have no interest in being ACID compliant and have chosen a different paradigm. And finally, this is kind of tongue-in-cheek, wait, but that's not how a database works. You may at some point find that the database just doesn't work the way that you expected it to. And that's why it's important to do as much homework as possible before you implement it. And that's why I created this guide. So one of the first questions I like to ask when I'm implementing something new is to ask, what if we succeed? And I don't think people ask that question enough. A lot of times people say, well, we don't have 1 million customers yet, so let's just cross that bridge when we get to it. But I think asking the question, what if you succeed, is very important for later on down the road so that you don't incur a lot of technical debt as you go. And one of the first things that I like to think about is there vendor support for the solution that you're looking to implement? In other words, who can you call if something goes wrong when all of your customers' data is unavailable? Are there commercial features available like encryption or in-place rolling upgrades to reduce downtime when you're actually up and running in production? And also, in terms of community involvement, is the solution being actively developed, or have the developers moved on to something else? Is there a large pool of experienced users to consult in forums or other venues? Or are you going to be one of just a handful of people implementing the database? And finally, are there specialists that you can hire? At some point, the databases and the data may grow beyond the point which it becomes just a part-time job, and you should ask, can you hire somebody to manage it for you? So the first place that I like to look when looking at software solutions is Gartner's Magic Quadrant. It's a really useful reference that I've used over the last few years, and even if I don't pick sort of the software vendors that are in the top right corner, it's also useful to know where they stand in relation to others. In 2017, Gartner changed their methodology and they excluded some smaller companies for this operational database management system categories. And they excluded MongoDB and Redis Labs, and I think DataStax as well. So I'm using a slightly old version, but I still think that it shows, sort of relatively speaking, where the different vendors are at. For this presentation, I chose to highlight MongoDB and Apache Cassandra. Mongo is supported by MongoDB Incorporated, which used to be called 10gen. And DataStax supports DataStax Enterprise. They used to also support an open source distribution, which they basically packaged and tested. They discontinued that, but they gave the source code to the Apache Cassandra Foundation. Just to be sure that my information was still relevant in the last couple years, here's another chart from Forrester called Forrester's Wave, which shows that the vendors are still pretty high up there in terms of their relevance. Also here on DB Engine's website, you can see MongoDB and Cassandra are pretty popular. They're not both in the top 10, but Mongo is, and Cassandra's pretty close. So the first database I'd like to highlight is MongoDB. It's a NoSQL document-oriented database. It has a JSON-like format for each document. It's actually BSON, which is a superset of JSON. It uses a JavaScript interpreter, so the syntax is familiar for doing the queries, but it also allows you to do server-side JavaScript execution in the database. It has a pluggable storage engine architecture. Right now, Wired Tiger is the only on-disk format that I know of right now. They used to have an mmap based storage engine, but they've discontinued it. There's also a commercial in-memory database, and it has a very flexible clustering architecture as well, where you can create replica sets or sharded clusters. Data in MongoDB is stored in databases. The databases are comprised of collections, which are equivalent to tables, and documents inside the collections. The documents have a flexible schema. They are not schemaless. If you don't create a schema, then it's very difficult to create indexes to query your data efficiently. As I mentioned, the format is BSON. So basically, when you look at documents, they look like JSON documents with some added features. In databases, it's typically important to understand how data is created, read, updated, and deleted. So I've included some examples of each of those methods for manipulating data in the databases. In this case, this is an example of a create statements where the first one inserts one document and the second one can insert many documents. Here's a read operation, basically a find with two documents as options. Here's an update. Again, here's update one instead of update many. There are different ways of updating data. This is just one example. And here's a delete, also just one document. In its simplest incarnation, MongoDB can run as a standalone database. Think of how you might run MySQL as a standalone without a replica. But this is typically only used for development. It doesn't have any high availability features. It doesn't have replication. You've got to back it up. And it's so easy to get more features that people just don't run it in this mode, except just for development purposes. So usually what you do is you create a replica set. Adds high availability. There are lots of advantages. The client writes to the primary. The primary is the master. The secondaries replicate data from the master. There's an option that if one secondary gets far behind, it can replicate from a more up-to-date secondary. Clients can read from secondaries, and you can also extend this to more complex configurations. For example, you can add disaster recovery with a remotely located hidden replica. If you lose an entire data center, the hidden replica can be used to create a whole new cluster, a new replica set. You can add a rollback feature with delayed replication. Basically, you can say, I want this replica to be 30 minutes behind all the other replicas. So if we deploy an update to the database, we have a way to get back to where we were 30 minutes ago. You can also do things like add an arbiter just to increase the number of votes that you have. so that you can always maintain a quorum of votes in the circumstance where one of the nodes goes down and you don't want to actually have an entire server doing replication. Now, the other configurations were vertically scaled configurations where basically Mongo could only hold as much data as any one node. In order to horizontally scale Mongo, you basically have to use a whole different paradigm. First, you need these Mongo routers that the clients connect to. The routers basically route traffic from the configuration servers, which have metadata in them, to the different sharded replica sets. So in this case, there's 3 shards. They're all replica sets, and basically data is balanced in between them. And it's quite a complex setup, not just architecturally like this, but also for authentication, authorization, because the config servers have different passwords and usernames than the replica sets. So there's a lot of stuff going on here, and it can get pretty complicated pretty fast. Imagine this is just representing basically one data center. Imagine if you have different geographically distributed data centers and databases, and they're all connected together. As you can see, Mongo gets pretty complicated. There are some things to keep in mind if you're going to implement Mongo. The first is schema design. There's a tendency when you first get started to think that Mongo documents don't have schemas, but schemas are actually a very important part of maintaining a healthy Mongo database. You create indexes based on the schema, and you create indexes to optimize query patterns to get the best performance out of the database. If every document is formatted differently, it's very hard to create efficient indexes, and also hard to optimize your query patterns with those indexes. You also need to avoid large objects like very large documents and using very large arrays inside those documents. Another area where people get into trouble is not turning on all the security features. Sometimes security is difficult when you're just trying to get your project up and running, but I would encourage you to use authentication, authorization, and encryption as early as possible, just so that you understand all the data models, role-based authentication, stuff like that. Another thing to keep in mind is that Mongo is accent and case sensitive, so you should probably keep in mind if you need to use accent and case insensitive collation that you need to think about that kind of when you first get started. And another area is don't turn off journaling. So there is a tendency sometimes for people to turn off journaling because the writes become very fast, but you can also lose data very fast as well. Now, because that's just a brief overview of Mongo, I wanted to include some resources here. MongoDB has great documentation. They also have MongoDB University, where they have training paths where you can take developer and DBA training paths, which lead to certifications. There's an O'Reilly book called MongoDB, The Definitive Guide. I would say before you implement MongoDB, you should probably follow one of the MongoDB University training paths and probably read at least MongoDB, The Definitive Guide, and other books out there if you find them useful. The second case study is Cassandra. Cassandra is a NoSQL wide column store. It's based on the distribution design of Amazon Dynamo. It was first developed at Facebook. It uses a data model similar to Google's Bigtable. It's distributed and highly scalable. It has a masterless model, no single point of failure. Every node can service any request. It has multi-data center replication. It has eventual and tunable consistency, meaning that it is eventually consistent and you can tune the different consistency levels. It does not use JavaScript or SQL. It uses its own query language called CQL. Data in Cassandra is organized into key spaces, which contain the replication factor. They also define the replication strategy. So is data just replicated locally, or is there a network topology that defines how the data gets replicated to other data centers, other geographically distinct locations? And the key spaces are tables. The tables have names. They're composed of rows, and they define which column has the primary key. Now, the columns are not the same as in a relational database because the names and format of the columns can vary from row to row, even in the same table. And that said, inside the tables are also rows. Just like Mongo, Cassandra has create, read, update, and delete operations. Here's a create operation. It looks similar to SQL, but it is not SQL. Again, here's a read, a select. Looks similar, but it is not SQL. Here's an update, and here's a delete. Because Cassandra has a masterless design, there are a lot of different layouts for the cluster that you can have. Basically, Cassandra is organized into clusters, data centers, racks, and nodes. In this scenario, with a simple ring topology, there's one data center and one rack. In any data center, you should have 3 seed nodes. Seed nodes are pretty much the same as other nodes, except they can provide hints as to what data is valid when the cluster first starts up. And I picked 4 nodes as being the minimum size I would recommend, just because you're supposed to have 3 seed nodes per data center, and not all of the nodes should be seeds. And also 4 nodes allows for a replication factor of 3, with 1 node being down. And sometimes you've got to do maintenance on a node or something like that, or sometimes nodes just crash. So I would recommend 4 being the smallest, although I've seen 2 node rings, and 3 node rings are pretty common as well. Now, in increasing complexity, Cassandra also supports a rack topology. So if in a data center you have racks of servers, the idea is that you don't want to replicate all of your data in the same rack. So if the power goes out, or a sprinkler bursts and rains down on any one rack, you still have the data in the other racks. Now, at this point, the replication strategy gets a little more complex. There are different sorts of replication strategies defined by what they call snitches. There are multiple types of snitches, and they're configurable. And so the details aren't important right now, but just keep in mind that you do have a lot of options in terms of understanding that you can define how the data is stored in different physical locations in the same data center. Now, going to data center topology, you see things can get really, really complex, where you have potentially 3 or more different physical locations. There can be different numbers of racks, different numbers of servers in every data center. And you really have to start wondering, how do you want to organize the data? Do you want to have every key space replicating to all the racks, or some of the racks, some of the data centers, all of the data centers? Which data centers have cheaper servers? There's a lot of options, and you're really going to need to spend time thinking about that once you get to this scale of implementing Cassandra. Just like with Mongo, there are some things to keep in mind if you're going to implement Cassandra. First is CQL is not SQL, and that similarity can be confusing. It's really easy to write some queries based on SQL knowledge, but it's also very difficult in other cases where knowledge of Cassandra internals is required for even simple operations. There are no joins, subqueries, or aggregates. There are tables, with rows and columns, but it is not relational. Um, in many cases, you want to denormalize the data to optimize queries, which is really antithetical to the relational model. You need to worry about compaction and repairs, which are essential aspects of managing Cassandra, but poorly understood. They're very important to deleting data. Basically, when you delete data, it creates tombstones where you tell Cassandra where you want the data to be deleted from. If you get too many tombstones, it can impact performance. If, for example, a node is down for too long and it hasn't undergone compaction or repairs, tombstones can expire, which resurrects data. When you delete data from a database, I don't think anyone would assume that the data would come back and be resurrected, but it can happen in Cassandra. Um, and the last thing here is developers define the consistency in code, which is actually tricky in practice because you can make mistakes where you assume that consistency worked one way, but it didn't. That can lead to bugs, and changing specifications can mean that assumptions made at one point are no longer true later, and it's possible to miss updating code to meet those changing specifications. Like Mongo, there are also resources available for Apache Cassandra, first from the Apache website. And also DataStax has training. And like with Mongo, the training can lead to industry certifications. And there's a developer and administrator track. There's also an O'Reilly book. I suggest reading the O'Reilly book before you try to implement Cassandra. So those are two databases you can install and configure yourself and manage yourself. What about managed cloud services? They reduce operational overhead, but they do not manage your data for you. The system can suggest, but they typically would not or could not optimize your queries for you. Are the managed services creating indexes for you? Are they doing other database optimizations based on your query patterns? What about data governance? Is there a facility by which they can basically age out data that's no longer needed? Will they delete data if a customer cancels their subscription? And finally, there's cost. A lot of times when you use a managed cloud service, you trade operational management costs for cost management. And finally, what about internet and web scale databases? And this is an interesting area of globally distributed databases. There are three I've included here: Amazon Aurora, and Microsoft Cosmos DB, and Google Cloud Spanner. I believe actually in these cases, Aurora and Spanner are relational databases, which makes it very interesting because the distributed databases typically aren't relational, but vendors are looking really deeply into making relational databases accessible for some of the reasons that I talked about earlier, and because people just have a lot of experience and they like using relational databases. So some final thoughts here. I picked Cassandra and Mongo, but I didn't want it to really be about any particular database. Really, I wanted to show that both Mongo and Cassandra and other databases have a lot of resources and a lot of options for vertical and horizontal scaling. There are lots of other options, and you should definitely take a look if you're going to implement something that needs a database. All databases are complex. It's important to learn to know what you don't know before you implement a solution. Mongo and Cassandra are both good solutions. And I read a quote where someone said, disappointment in them can only come from comparing them to a relational database. And I think that's true. They're both evolving and they're both improving all the time. I've worked with both of them and I think they're great solutions. And finally, I wanted to say, before you put your data into a database. Understand your data. How important is it? Does it need to be highly durable, highly consistent? And spend time on your data model, thinking about your data model before you start writing a lot of code. Um, how do you want to organize the data? What sorts of schemas are you going to need? How should you organize it? And I think the more time you spend on that, the more luck you're going to have with any database, and the more you're going to understand the pluses and minuses of any database solution. Um, so those are my thoughts, and I hope this is useful for you, or at least interesting if you've never delved into any of these NoSQL databases. I encourage you, if you're interested, to take a look at some of the other ones. And with that, thank you for your time.